In continuum mechanics, stress is a physical quantity that expresses the internal forces that neighboring particles of a continuous material exert on each other, while strain is the measure of the deformation of the material. For example, when a solid vertical bar is supporting a weight, each particle in the bar pushes on the particles immediately below it. When a liquid is in a closed container under pressure, each particle gets pushed against by all the surrounding particles. The container walls and the pressure-inducing surface push against them in reaction. These macroscopic forces are actually the net result of a very large number of intermolecular forces and collisions between the particles in those molecules. Strain inside a material may arise by various mechanisms, such as stress as applied by external forces to the bulk material or to its surface. Any strain of a solid material generates an internal elastic stress, analogous to the reaction force of a spring, that tends to restore the material to its original non-deformed state. In liquids and gases, only deformations that change the volume generate persistent elastic stress. However, if the deformation is gradually changing with time, even in fluids there will usually be some viscous stress opposing the change. Elastic and viscous stresses are usually combined under the name mechanical stress. Significant stress may exist even when deformation is negligible or non-existent. Stress may exist in the absence of external forces. Such built-in stress is important. For example, in pre-stressed concrete and tempered glass. Stress may also be imposed on a material without the application of net forces, for example by changes in temperature or chemical composition, or by external electromagnetic fields. The relation between mechanical stress, deformation, and the rate of change of deformation can be quite complicated, although a linear approximation may be adequate in practice if the quantities are small enough. Stress that exceeds certain strength limits of the material will result in permanent deformation or even change its crystal structure and chemical composition. In some branches of engineering, the term stress is occasionally used in a looser sense as a synonym of internal force. For example, in the analysis of trusses, it may refer to the total traction or compression force acting on a beam, rather than the force divided by the area of its cross-section. History. Since ancient times, humans have been consciously aware of stress inside materials. Until the 17th century, the understanding of stress was largely intuitive and empirical, and yet it resulted in some surprisingly sophisticated technology, like the composite bow and glass blowing. Over several millennia, architects and builders, in particular, learned how to put together carefully shaped wood beams and stone blocks to withstand, transmit, and distribute stress in the most effective manner. With ingenious devices such as the capitals, arches, cupolas, trusses and the flying buttresses of Gothic cathedrals, ancient and medieval architects did develop some geometrical methods and simple formulas to compute the proper sizes of pillars and beams. But the scientific understanding of stress became possible only after the necessary tools were invented in the 17th and 18th centuries. Galileo Galilei's rigorous experimental method, René Descartes' coordinates and analytic geometry, and Newton's laws of motion and equilibrium and calculus of infinitesimals. With those tools, Augustin Louis Cauchy was able to give the first rigorous and general mathematical model for stress in a homogeneous medium. Cauchy observed that the force across an imaginary surface was a linear function of its normal vector, and, moreover, that it must be a symmetric function. The understanding of stress in liquids started with Newton, who provided a differential formula for friction forces in parallel laminate of flow. Overview. Definition. Stress is defined as the force across a small boundary per unit area of that boundary, for all orientations of the boundary, being derived from a fundamental physical quantity and a purely geometrical quantity. Stress is also a fundamental quantity, like velocity, torque or energy, that can be quantified and analyzed without explicit consideration of the nature of the material or of its physical causes. Following the basic premises of continuum mechanics, stress is a macroscopic concept, namely, the particles considered in its definition and analysis should be just small enough to be treated as homogeneous in composition and state, but still large enough to ignore quantum effects and the detailed motions of molecules. Thus, the force between two particles is actually the average of a very large number of atomic forces between the molecules, and physical quantities, like mass, velocity, and forces that act through the bulk of three-dimensional bodies, like gravity, are assumed to be smoothly distributed over them. Depending on the context, one may also assume that the particles are large enough to allow the averaging out of other microscopic features, like the grains of a metal rod of the fibers of a piece of wood. Quantitatively, the stress is expressed by the Cauchy traction vector T, defined as the traction force F between adjacent parts of the material across an imaginary, separating surface S, divided by the area of S. In a fluid at rest, the force is perpendicular to the surface, and is the familiar pressure. In a solid, or in a flow of viscous liquid, the force F may not be perpendicular to S, hence the stress across a surface must be regarded a vector quantity, not a scalar. Moreover, the direction and magnitude generally depend on the orientation of S. Thus, the stress state of the material must be described by a tensor, called the stress tensor, which is a linear function that relates the normal vector n of a surface S to the stress d across S. With respect to any chosen coordinate system, the Cauchy stress tensor can be represented as a symmetric matrix of 3 times 3 real numbers. Even within a homogeneous body, the stress tensor may vary from place to place, and may change over time. Therefore, the stress within a material is, in general, a time-varying tensor field. Normal and shear stress in general. The stress d that a particle P applies on another particle Q across a surface S can have any direction relative to S. The vector T may be regarded as the sum of two components, the normal stress perpendicular to the surface, and the shear stress that is parallel to the surface. If the normal unit vector n of the surface is assumed fixed, the normal component can be expressed by a single number, the dot product Tn. This number will be positive if P is pulling on Q, and negative if P is pushing against Q. The shear component is then the vector T minus n. Units. The dimension of stress is that of pressure, and therefore its coordinates are commonly measured in the same units as pressure, namely, pascals in the international system, or pounds per square inch in the imperial system. Because mechanical stresses easily exceed 1,000,000 pascals, MPa, which stands for megapascal, is a common unit of stress. Causes and effects. Stress in a material body may be due to multiple physical causes, including external influences and internal physical processes. Some of these agents act on the bulk of the material, varying continuously with position and time. Other agents may create stresses and forces that are concentrated on certain surfaces, planes, or points, and possibly also on very short time intervals. In general, the stress distribution in the body is expressed as a piecewise continuous function of space and time. Conversely, stress is usually correlated with various effects on the material, possibly including changes in physical properties like birefringence, polarization, and permeability. permeability. The imposition of stress by an external agent usually creates some strain in the material, even if it is too small to be detected. In a solid material, such strain will in turn generate an internal elastic stress, analogous to the reaction force of a stretched spring, tending to restore the material to its original underformed state. Fluid materials by definition can only oppose deformations that would change the volume. However, if the deformation is changing with time, even in fluids there will usually be some viscous stress opposing the change. The relation between stress and its effects and causes, including deformation and rate of change of deformation, can be quite complicated. Stress that exceeds certain strength limits of the material will result in permanent deformation or even change its crystal structure and chemical composition. Stress analysis. Stress analysis is a branch of applied physics that covers the determination of the internal distribution of internal forces in solid objects. It is an essential tool in engineering for the study and design of structures such as tunnels, dams, mechanical parts, and structural frames, under prescribed or expected loads. It is also important in many other disciplines, for example, in geology, to study phenomena like plate tectonics, volcanism and avalanches, and in biology, to understand the anatomy of living beings. Goals and assumptions. Stress analysis is generally concerned with objects and structures that can be assumed to be in macroscopic static equilibrium. By Newton's laws of motion, any external forces are being applied to such a system must be balanced by internal reaction forces, which are almost always surface contact forces between adjacent particles, that is, a stress. Since every particle needs to be in equilibrium, this reaction stress will generally propagate from particle, creating a stress distribution throughout the body. The typical problem in stress analysis is to determine these internal stresses, given the external forces that are acting on the system. The latter may be body forces, that act throughout the volume of a material, or concentrated loads, that are imagined to act over a two-dimensional area, or along a line, or at single point. In stress analysis, one normally disregards the physical causes of the forces of the precise nature of the materials. Instead, one assumes that the stresses are related to deformation of the material by known constitutive equations. Methods. Stress analysis may be carried out experimentally by applying loads to the actual artifact at a scale model and measuring the resulting stresses by any of several available methods. This approach is often used for safety certification and monitoring. However, most stress analysis is done by mathematical methods, especially during design. The basic stress analysis problem can be formulated by Euler's equations of motion for continuous bodies and the Euler-Cauchy stress principle, together with the appropriate constitutive equations. Thus, one obtains a system of partial differential equations involving the stress tensor field and the strain tensor field as unknown functions to be determined. The external body forces appear as the independent term in the differential equations, while the concentrated forces appear as boundary conditions. The basic stress analysis problem is therefore a boundary value problem. Stress analysis for elastic structures is based on the theory of elasticity and infinitesimal strain theory. When the applied loads cause permanent deformation, one must use more complicated constitutive equations that can account for the physical processes involved. However, engineered structures are usually designed so that the maximum expected stresses are well within the range of linear elasticity, that is, the deformations caused by internal stresses are linearly related to them. In this case, the differential equations that define the stress tensor are linear, and the problem becomes much easier. For one thing, the stress at any point will be a linear function of the loads. 2. For small enough stresses, even non-linear systems can usually be assumed to be linear. Stress analysis is simplified when the physical dimensions and the distribution of loads allow the structure to be treated as one- or two-dimensional. In the analysis of trusses, for example, the stress field may be assumed to be uniform and uniaxial over each member. Then the differential equations reduce to a finite set of equations with finitely many unknowns. In other contexts, one may be able to reduce the three-dimensional problem to a two-dimensional one, and/or replace the general stress and strain tenses by simpler models like uniaxial tension, compression, simple shear, etc. Still, for two or three-dimensional cases, one must solve a partial differential equation problem. Analytical or closed-form solutions to the differential equations can be obtained when the geometry, constitutive relations, and boundary conditions are simple enough. Otherwise, one must generally resort to numerical approximations such as the finite element method, the finite difference method, and the boundary element method.